In this video, I would like to review the concepts of the work-energy theorem and the principle of the conservation of energy. First, let's start with the work-mechanical energy theorem. The total work done by a body equals the change in mechanical energy. Or more specifically, the total work done includes the work done of all the conservative forces acting on the body. Now you're probably wondering, what's a conservative force? So let me give you a little bit more detail. Conservative forces are forces that have potential energies, basically stored energies associated with them. For example, weight, or the gravitational force, is a conservative force since you can store the energy of an object when it's in a gravitational field. When the object moves up, you are essentially lifting it against the gravitational field, and you're storing that energy within the field. Now, that stored energy is easily recovered. For example, if you let the rock, for example, just fall straight down, then the object will pick up speed and it'll turn that stored gravitational potential energy into kinetic energy. Other forces, such as the elastic force, or gravitational force, electric and magnetic forces, are also conservative forces. However, not all forces are conservative. For instance, friction, viscous drag, and air resistance are non-conservative forces. Well, let me put it this way. Friction, there is no sort of frictional potential energy. You see, when the kinetic friction does work on, say, like a box that is moving across a floor and there's friction acting on the object, well, the energy that is dissipated from the system is converted into a sort of a disorganized or chaotic form, such as thermal energy, which is not easily recovered as kinetic energy. We'll get into much more detail with the cases where you have work being done by friction, for example, which you have, in this case, what we call a non-conservative force system. And you'll see that later in the notes, like page 13 or something like that. For systems of objects or particles where you only have conservative forces, so you don't have any non-conservative forces, there's no friction in the system, then we will be looking at what is known as mechanical energy. So you only really have essentially kinetic energy, which is that moving energy, and all the different potential energies associated with that particular body or the system of bodies. Now, the sum of the kinetic energy and the potential energies of the system or body is called the mechanical energy. You can abbreviate that with an ME, or you can simply just write it as just E. Okay, so on the AP notation, we tend to use E equals K plus U. But in some other places, you might see ME written as KE for kinetic energy plus PE for potential energy, which obviously makes sense as abbreviation. But this is the way that it's written typically on an AP exam. So this means the total mechanical energy is equal to the sum of the kinetic energy and potential energies. Now, back to our work mechanical energy theorem, which states that the total work done by a body is equal to the change in mechanical energy. So essentially what we're saying is that total work done is equal to the sum of the kinetic energies plus the potential energies. And a very important point to realize, conservative forces, such as the elastic and gravitational and electric and magnetic forces that have associated potential energies with them, they don't change the total energy of the system or body. They only change it from one form to another. So it could be changing, say, from potential energy into kinetic energy. So conservative forces do not change the total mechanical energy. They just change it from one form to another, which essentially means the following, that the work done, the total work done, in a system where you only have conservative forces is equal to the total change of that energy. But the total change of that energy, which is kinetic and potential, it's not changing, only changing from one form to another. So essentially, that change in energy is equal to 0. And when you're finding the change in energy, it's really just the final energy at some particular point minus the initial energy, which we'll write with E sub I. So that difference in the energies will be equal to 0, which then really means that the energy initially is equal to the energy finally. So this statement right here, when you write that down, then you're essentially saying that if you have a system of just conservative forces, then the total energy initially of the system is equal to the total energy afterwards when it goes through, say, some process. So the sum of those energies, which is kinetic and potential, stays constant. So we often write it this next line that you see here right after you write that. Now when you write this is very important that you write this in your problems because you're essentially saying, I am assuming that this is a system of only conservative forces and the total energy remains constant. And then by writing the next line, you're saying, I know that energy is made up of kinetic and potential energies. And then you could then go into putting these appropriate terms, like kinetic energy is 1/2 mv initial squared. And if you're just dealing with gravitational potential energy as the potential energy, then you would have just an mgh initial. And then for the final kinetic energy, you could write 1/2 mv final squared. And then for the final potential energy, you could simply write just mgh final. And I'd also like to add one more point to this video, a point regarding choosing the appropriate coordinate system. You see, when we dealt with kinematics problems, let's say you had like an object that was fired off at an angle off of the top of a cliff and then lands here at the base. Before you proceeded into solving the problems of the kinematics equations, I asked you to always choose an appropriate coordinate system. You'd lay down possibly your y-axis like that and your x-axis over here, and you would maybe make the initial height here whatever the height of the cliff was. And then when the ball comes, say, over here and just about to hit the ground, then you would say that the final height vertically would be 0. Well, the same thing applies with conservation of energy problems. You can choose where you would like to assume 0 potential energy. My usual preference is to choose the lowest point, say right here, to have 0 potential energy. And so when I solve problems, I might go over here and just say this height at that location is 0, so that when I look at the potential energy finally, which is mgh final, the final height is 0, so that term goes to 0. And then this height initial is whatever this height of the cliff was. You can really set your 0 potential energy at any convenient location. It really doesn't matter. In fact, if you go on to say another part within the question, you can reset it to a different point if it's more convenient. Okay, that's it for this video.